figure shows a single line diagram of three-phase power system, and select a common base of 100 MVA and 22 kV for base voltage on the generator side. Draw the impedance diagram with all impedance including the load impedance marked in per unit. The first procedure for per unit calculation is to determine different region. Given base power equal to 100 MVA and the base voltage is equal to 22 kV on the generator side. So for this case, we have region number 1, region number 2, region number 3, and region number 4. So now we need to find the base voltage for all sections or for all regions of the power system network. For the first region, which is on the generator side, the base voltage V base 1 on the low voltage of transformer T1 is equal to 22 kV. For region number 2, V base 2 on the high voltage side of T1 is equal to V base 1 multiply with V from secondary side divided by voltage from the primary side. So we know that V base 1 is equal to 22 kV, and then voltage from the secondary side of T1 is equal to 220 kV, and voltage from the primary side of T1 is equal to 22 kV. Thus, we get V base 2 is equal to 220 kV. We can also calculate V base 2 on the high voltage side of T2, and we will find similar answer, which is 220 kV. Now we can calculate the base voltage for region number 3. The base voltage for region number 3 on the high voltage side of T3 is equal to base voltage from region 1 multiply with the secondary voltage of T3 divided by the primary voltage of T3. So base voltage for region 1 is equal to 22 kV multiply with 110 kV, which is the secondary voltage of transformer T3, divided by 22 kV, which is the primary voltage of transformer T3. So we get the answer for the base voltage of for the V base 3, which is equal to 110 kV. Similarly, we can also find the base voltage for region number 3 on the high voltage side of T4, and we will get the same answer, which is 110 kV. For region number 4, the base voltage for region number 4 on the low voltage side of T2 is equal to V base 2 multiply with V2 divided by V1. So V base 2 is equal to 220 kV multiply with the secondary voltage of T2 is 11 kV, and the primary voltage of T2 is 220 kV, and thus we get the base voltage at region number 4 is equal to 11 kV. Similarly, we can also calculate the base voltage for region number 4 on the low voltage side of T4, which is equal to V base 3 voltage base from region number 3 multiply with secondary voltage of transformer T4 divided by primary voltage of transformer T4. So base voltage for region 3 is equal to 110 multiply with 11 kV divided by 110 kV, and we can see that we get the similar base voltage whether we refer on low voltage side of T2 or we refer on the low voltage side of T4. So we get similar results for base voltage for region number 4, which is equal to 11 kV. To calculate the per unit impedance for the generator and transformers, we use the formula. The new impedance in per unit is equal to the old impedance in per unit multiplied with the new base power divided by the old base power multiplied with the old base voltage divided by the new base voltage squared. Since the generator and transformer voltage base are the same as their rated values, so we can eliminate this part because VO is equal to V1, so this part is equal to 1. So 1 to the power of 2 is equal to 1, so we can cancel this part and we can use this formula, which is the new impedance in per unit is equal to the old impedance in per unit multiplied with the new base power divided by the old base power. So we can use this formula to find the new per unit impedance for the generator and transformer. So the new per unit impedance for generator is equal to the old per unit impedance of the generator, which is 0.18 multiplied with 100 MVA divided by the old base power of the generator is equal to 90 MVA. So we get J 0.2 PU, and then we calculate for the new per unit impedance of transformer T1 which is equal to J 0.10 multiplied with 100 divided by 50 MVA. 50 MVA is the old base power of the transformer T1. So we get J 0.2 PU. And then for transformer T2, the new per unit impedance is equal to J 0.06 PU multiplied with 100 MVA divided by 40 MVA, which is equal to J 0.15 PU. And then for transformer T3, the new per unit impedance is equal to the old per unit impedance, which is equal to J 0.064 multiplied with 100 MVA, which is the new base power, divided by 40 MVA, which is the old base power, which this is equal to J 0.16 PU. And for the transformer T4, ZT4 in per unit is equal to the old per unit impedance, which is J 0.08 multiplied with 100 divided by 40 MVA. So we get J 0.2 PU. The new impedance of the motor load is equal to the old impedance in per unit multiplied with the new base power divided by the old base power multiplied with the old base voltage divided by the new base voltage square. And we know that the old impedance of the motor load is equal to J 0.185 PU. The new base power is 100 MVA. The old base power is 66.5 MVA. And then the new base voltage is equal to 11 kV, and this is actually equal to the base voltage at region number 4 because the motor is located at region number 4. And then the all base voltage is equal to 10.45 kV. And we put all these values into this equation, and thus we get the new impedance for the motor load in per unit, which is equal to J 0.25 pu. For transmission line, for the line 1, we have base voltage is equal to 220 kV and the base power is equal to 100 MVA. Thus, we can calculate for the base impedance. So, Z base for line 1 is equal to V base for region number 2 because the transmission line for line 1 is located at region number 2 divided by S base. So at region number 2, the voltage base is 220 kV square divided by 100 MVA, and thus we get 484 ohm. And then for line number 2, the base voltage for transmission line 2 is equal to 110 kV and the base power is 100 MVA. The transmission line 2 is located at region number 3. So Z base for line 2 is equal to V base for region number 3 square divided by S base. So this is equal to 110 kV square divided by 100 MVA, and we get the base power, the base impedance for line 2 is equal to 121 ohm. The per unit impedance of transmission line 1 ZPU for line 1 is equal to Z actual divided by Z base. So the actual impedance is equal to J 48.4 ohm. So this is actually the actual impedance due to inductance at transmission line 1 divided by the Z base, which is 484 ohm. And thus we get the impedance in per unit for transmission line 1 is equal to J 0.1 pu. And for transmission line 2, the per unit impedance is equal to Z actual divided by Z base, and Z actual is 65, J 65.43 divided by 121 ohm. So this is equal to J 0.54 pu. Given the three-phase load S is equal to 57 MVA at 0.6 power factor lagging at 10.45 kV, and thus theta is equal to cos inverse 0.6, which is equal to 53.13 degree. And we can calculate for the three-phase load. and this is equal to 57, and the angle is 53.13 degree MVA, and therefore the Z load actual is equal to V line to line square divided by S load conjugate 3-phase. Hopefully you have already learned this part in the circuit analysis too. So the V line to line is 10.45 kV square divided by 57 angle minus 33.13 degree MVA. So this is equal to 1.1495 plus J 1.53267 ohm. So we need to put minus here because of conjugate here. And then calculate for the base value for the load, which is equal to V base at region number 4 square divided by the base power. So V base at region number 4 is equal to 11 kV divided by 100 MVA. So we get the base value for the load impedance equal to 1.21 ohm. And thus the load impedance is equal to the actual value divided by the base value. So the actual load is 1.1495 plus J 1.53267 ohm divided by the base value at region number 4, which is 1.21 ohm. And this is equal to 0.95 plus J 1.2667 pu. And finally, we need to draw the per unit impedance diagram. So from the per unit calculation that we have done earlier, so this is the per unit impedance diagram for the single line diagram in this example.